Okay, thank you, Florent. I would like to thank the organizers. It's a very nice program and very nice to be here. So I'll talk about a sort of new proof technique that we have developed in the last years that we call spatial coupling. And this was developed through joint work mainly with Rudiger and Andrei Georgiou, but also through other works with Dimitris Aklioptas, Hamed Afani, Santosh, Kumar, Andrew Jung, and Henry Pfister, and also Srinivas a few years ago. Okay, so what is spatial coupling? Spatial coupling originated as an engineering construction in coding theory for building error-correcting codes for communications. And it's quite old from this point of view. I mean, it dates back to 1999. And I don't know exactly the history very precisely. Rudiger can tell you more, but maybe it was not, people didn't realize how nice this construction was at first. And well, finally, with progress that was made in theory, it was realized that spatially coupled codes achieve the Shannon capacity for a wide class of memory-less channels. So I'm talking about LDPC codes, and that we are going to spatially couple. I'll explain what this is. Now, for today, my goal is not to construct very good LDPC codes. I'll study standard LDPC codes. However, I want to determine exactly their thresholds. So what is if you wish, the capacity for these codes, for the standard codes. And so we want to determine the information theoretic limits of these standard LDPC codes. And I'm going to use spatial coupling, but as a proof technique. And in general, it's a proof technique that allows you to derive properties of graphical models that have nothing to do with this construction per se. Okay, so it's like when you use complex analysis to prove something in real analysis. You do a detour. Okay, so as I said, I'll focus on one application, which is, for those who know what this means, it's the proof of the replica symmetric formula for the mutual information of LDPC codes, or it could have been low-density generator matrix codes. But this set of ideas goes much beyond coding theory. Florent already made some advertisement this morning. You can use it for a relatively wide, at least we think, wide class of inference problems. But also, if I have time, I'll mention briefly some new algorithmic bounds on constraint satisfaction problems like KSAT for low K. So I don't know if I'll have time, but we'll see. Okay, so Rudiger briefly explained what is an LDPC code. So let me, and also what's the problem of communication through a memory-less channel, but let me briefly set up the notation here. So LDPC stands for low density parity check. So you want to communicate a code word x1 through xn, which takes values in plus minus 1, and you communicate this through a memory-less channel. So that makes transition between the code bit xi that you send is received as a symbol yi. Q epsilon here is the transition probability matrix. So if you think of a typical channel is the binary symmetric channel where the arrival alphabet is plus minus 1. And so you flip the bit with probability epsilon and you don't flip it with probability 1 minus epsilon. Okay, so whatever I say is valid basically for all so-called binary memoryless symmetric channels, but think of this channel as a typical one. Okay, so these code bits that you send are correlated through parity checks here. that, so these are modulo 2 sums in the 0-1 language of the bits that are connected here. And in the language of +-1, in fact, the constraint that you enforce is that the product of the, I'll call them spins, of the spins that enter in the parity check should be equal to +1. So this model here, you can view it as a spin system. When you do inference, you want to decode according to the, say you want to decode according to the map optimal estimator. So you have to study this measure over the spins x given your channel observations y. And this measure is the measure of some kind of spin system where you enforce the constraints here. The product of the spins should be equal to +1, so this is the indicator function for this product. And you have a prior measure over the spins that in fact contains the channel, the knowledge that you have of the channel outputs. Okay, so the channel outputs yi are encoded or parameterized by this log likelihood ratio hi that you can think of as a magnetic field that acts on spins and has a tendency to polarize spins up or down. So that's your prior information. Okay, so the code has a rate that I will fix. The rate is fixed by 1 minus the ratio of the left degree to the right degree. The left degree is the degree of the so-called variable nodes here, and the right degree is the degree of the check nodes. So think of degree 3, 6, and 3, and 6 here, so the rate is 1/2, say. So what I want to do is to fix the degrees. So this corresponds to standard regular LDPC codes. And I want to look at phase transitions for this measure as the channel noise epsilon, the bit flip probability varies. Okay. So what kind of phase transitions do we have? We have two types of phase transitions, basically. One that I call static. It's the thermodynamic phase transition of statistical mechanics. It's the optimal threshold from the point of view of information theory. It's defined as follows. Epsilon map is the smallest value of epsilon such that the average over the ensemble of LDPC codes, I forgot to say, so these codes are drawn at random from some ensemble with fixed degrees for variable and nodes and check nodes. So this average Shannon conditional entropy of the input given the output, when it is strictly positive, you cannot decode, but when this vanishes in the asymptotic limit, you expect that you can decode. So there is a phase transition typically such that from 0 to epsilon map, you can decode. This average entropy vanishes, and above epsilon map, you cannot decode. This average entropy does not vanish. So if you're not used to Shannon entropy here, you can also think of H as the log of Z, so minus the free energy of this spin model. Okay, the second phase transition I want to discuss is an algorithmic phase transition, at least when you use message passing, so belief propagation. That's the maximum noise value such that the belief propagation decoder can recover the input. And certainly you have in general that the algorithmic threshold is less than the optimal threshold. However, the basic questions that I want to answer is, can one compute these thresholds exactly? Can one even compute this conditional entropy in the asymptotic limit? And can one do this even rigorously? Okay. So the main result here that I want to explain how we prove it with this proof technique, spatial coupling as a proof technique, combined with interpolation methods, is the following theorem. So I will need some technical conditions that say that, okay, the degrees of the code have to be constant, the degree of the parity checks has to be even, I will say why later, and also I have to take large enough degrees, but finite, fixed. That's still large enough. Okay. Under these assumptions, one can prove that this limit of the conditional entropy, the average conditional entropy, the average is over the code ensemble, is given by a variational problem, and this variational problem involves a functional of some probability density x that I don't specify for the moment. I'll specify it later. And what you should do is compute the supremum of this functional over this probability density. So now, for a few slides, I won't write down the formula because it's a bit complicated even to explain the formula, but later on I'll become a bit more technical and I'll give the formula in more details. But for the moment, we just need to know that the theorem says you can compute this as the supremum of some functional over some set of probability densities. And moreover, all the thresholds, not only the map threshold, but also the belief propagation threshold, is contained in this functional. So if you study this variational problem, you can completely determine the thresholds. Now, this functional was first computed by statistical physics method that goes under the name replica symmetric calculation, and so it's called the replica symmetric functional. I'll call it like this. And this was computed around the year 2000. Okay, so the predictions of this formula are the following. So basically, this curve here as a function of epsilon is a continuous function. So it is 0 from epsilon equals 0 up to epsilon map. That's the information theoretical optimum threshold. And then it's positive, but it's always continuous. Okay? So epsilon map is a point where the function is not analytic. Since it's 0 and then it's positive, at epsilon map, it's not analytic. So there is a question, what kind of non-analyticity do you have? Okay, so I'll be interested only in cases where, in fact, I have a first derivative in the jump of this function. I mean, a jump in the first derivative of this function, okay? And this is called the first order phase transition, and this is always the case, that the first derivative jumps when the degree of the variable nodes is greater or equal to 3. Okay, for L equal 2, for a degree 2, that's a special case where the phase transition is continuous, so it's a higher derivative that will jump. Okay, this case is also covered by our methods, but that's not the really interesting case that we want to cover. Okay, so now we will use in our proofs not only spatial coupling, but also older tools that have been developed. Okay, and there are two basic inequalities that have been known for a very long time. I mean, a long time means 10 years. So the first inequality, in fact, is a lower bound where that says that this quantity I'm after, this conditional entropy, is greater or equal than the sup of this replica symmetric functional. Okay, so of course for many years we've been frustrated because we could not prove the converse bound. And this thing here, you know, the methods to prove this bound, I won't show them, but they originate in work of Guerra and Toninelli and go under the name interpolation method. These are the bounds that were first proven for the SK model and then extended to sparse systems. These LDPC codes are spin systems on dilute graphs by Franz and Leone and Panchenko. And then this made its way into coding theory. Okay, The second bound is a kind of intuitive bound, although for codes it's not at all a trivial bound here. But basically it says that the map decoder is better than the belief propagation decoder. So mathematically you have the following thing. If you look at the derivative of this conditional entropy with respect to the noise of the channel and take the limit, this is less or equal than the partial derivative of this replica symmetric functional with respect to the noise. So in this object that I'll write later on, you have an explicit dependence with respect to the channel. So you can take this partial derivative with respect to this explicit dependence, but you also have an implicit dependence in the max. This soup in fact is attained, and in this max density that maximizes this, you have an implicit dependence. So I don't take the derivative with respect to this implicit dependence here. So, okay, well. In the case of the binary erasure channel, where a bit is sent and either it's received or it's erased, so that's a very simple channel, and Rudiger was talking about that channel. These two objects, they have a nice interpretation. In fact, this can be interpreted as the probability of error under map decoding, and this can be interpreted as the probability of error under BP decoding, and then the inequality is basically evident. However, for general channels, you don't quite have this interpretation as a probability of error here, so it's not a trivial inequality. From the point of view of spin systems, it can be viewed as a kind of correlation inequality for magnetizations. In coding theory, you find other proofs that take some different point of view. Okay, so now if we didn't have a phase transition in this problem, or if the phase transition was continuous, like for codes with degree 2 for the variable nodes, then just by combining these two inequalities, we could essentially close the gap here and get the equality, okay? So you get a lot of insight from this remark for what follows, so I just want to go through this remark. So suppose we didn't have a phase transition of first order, or no phase transition at all. Then what would happen is that with no phase transition, in fact, this replica symmetric functional would have a unique maximum, and as the noise varies, this maximum would vary continuously, but would not jump from one value to the other one. When you have a first order phase transition, it happens that this max can jump from one value to the other one. Now, if this max does not jump from one value to the other one, anyway, you can replace it by the so you can replace here. So the max obtained by the BP decoder, you can just replace it by the soup. So you can finally, and then you can replace this partial derivative by a total derivative. Okay, so the inequality without a phase transition, that's also true if you have a second order or higher order phase transition. You have here two derivatives, two total derivatives. Okay, and if you have two total derivatives, then basically you can integrate the inequality from 0 to epsilon on both sides, and you can do this integral. And then what you get is that, well, the integrand, I mean the thing inside the derivative at epsilon minus the thing at zero noise, but at zero noise this entropy is zero because you have perfect knowledge. So finally you get on the left-hand side this conditional entropy is less than what's in the derivative here, and this you can check explicitly at zero noise is also zero, so you get this inequality. But this, if you look at the Guerra type inequality here, is exactly the converse inequality sign. So with the two inequalities, you get equality. Okay. However, when you have a first-order phase transition, you cannot replace this partial derivative by a total derivative. Okay, so this doesn't work. Yeah, so maybe I should have shown this graph before. So that's exactly the case where I'll have a, so this is a cartoon picture of this replica symmetric functional that depends on densities here. Well, you can picture the density here as a real number. And so I plot minus the replica symmetric function. I call this a potential. Okay, like physicists prefer to plot minus this thing, so it's a potential. This as a function of x here. And you see, when you have a first order phase transition as a function of epsilon, this family of curves develops a local minimum here. And that's why you cannot replace what I was saying here, this belief propagation maximum. This belief propagation maximum corresponds to the local minimum, and you cannot replace it by the sup or by the true minimum. The true minimum is here at 0. Okay. When you go down to the map threshold corresponds exactly to the situation where the two minima are at the same height. So the true minimum jumps to this other value that takes over and becomes the new true minimum. So that's the first order phase transition. Okay. Now, with spatial coupling, in fact, what we will do is that somehow we will eliminate this local minimum. Okay. And by eliminating this local minimum, we'll be able to carry out basically this argument. Okay. So that's the first idea of how things work. So what is spatial coupling? Okay, so this construction, as I said, is an engineering construction, was introduced by Feldstrom and Zigangirov. And so what you do here is that, first of all, you align along a chain a certain number of LDPC code ensembles. So that's a cartoon picture for a set of 2L+1 LDPC code ensembles. So I have the variable nodes here and the check nodes here, and variable nodes have degree 3, check nodes have degree 6. Okay, so at each position you have a code ensemble, so you have to imagine here that you have a stack of variable nodes here in this direction and here, and this is just a cartoon picture for the edges that are connected along your graph that is here. So you align these graphs, and then you reconnect the edges so that the various codes here get coupled, but somehow you preserve the local degree structure. Okay, so this can be a technical construction, especially if the degrees are constant L and R. You have to satisfy a lot of constraints, so I won't explain this technical construction. What is important is that somehow you have more check nodes at the boundary here, so the bits that are at the boundary are more constrained, so they are better protected. Okay, so intuitively, when you are going to run the belief propagation decoder, these bits at the boundary will help you. Okay, the checks here at the boundary will help you because these bits are better protected, and these bits act as a kind of seed that allow to find the code word at the boundaries, and then you sort of find the code word by entering. I mean, the seed propagates inside the system, and you can decode. Okay, so that's just an intuition, but this intuition tells you that basically, you know, the correct minimum of the of this replica symmetric functional will propagate inside the system, okay? And in the bulk, maybe you are stuck at the wrong minimum, but somehow, if you propagate the correct minimum, so suppose the noise is fixed and you have this functional here, this potential functional. If the correct minimum that is at 0 propagates inside the system, and in the bulk you are stuck here, the effective potential that drives the decoding during decoding, in fact, you should really think of it as a kind of convexification of this potential. So your effective energy here is a convex combination of this point and this point. Okay, so you have effectively a convexification of this potential, and so you can find always the correct minimum. That's also one way to think about the problem, and that's called the Maxwell construction in physics. Okay, so that's what I'm saying here. For these codes here, the local mean for the entropy, it's a local max, so sometimes I change words between max and mean, but this local thing disappears, the metastable states disappear, and the new BP threshold, the new algorithmic threshold of the coupled codes becomes basically equal to the optimal threshold, okay? Because if you think about it, if you convexify this curve here, well, if you draw a tangent here, when you increase epsilon, you will reach, these tangents will reach the horizontal here line, and there is no more BP threshold, in fact, okay? Or the BP threshold is exactly equal to the map threshold when the tangent becomes horizontal. Okay, so that's a basic intuition. Now, I want to make all this more quantitative, so it's going to become a bit more technical now. Okay, so to make things more quantitative, I just need to introduce a few definitions here. So let me first describe the belief propagation algorithm. So the belief propagation algorithm we already saw in this conference, in fact, exchanges messages along the edges of the graph according to some update rules here. And thanks to these update rules, you compute an effective log likelihood associated to bit I that you want to decode. And with this log likelihood, you can compute a kind of marginal of your measure, that's the BP marginal, and then you take your decision according to this marginal, whether this HI at time t is positive or negative. You fix the bit to +1 or -1. Now, this algorithm is tracked by something called density evolution. So density evolution tracks the density of messages along the edges of the graph. Okay, so this x, in fact, is exactly the density that I have in my replica symmetric functional over which I have to optimize. But here, it has nothing to do with this replica symmetric functional for the moment. It's just the density of the messages along the graph, and this density satisfies the density evolution equation, which in fact is written here in a rather abstract way, but what it means here is that you make a convolution L-1 times that corresponds to this sum here, and then there is another sort of boxed convolution operation R-1 times that corresponds to this product of hyperbolic tangents and arctangent here. And then there is a final convolution with a channel density, which corresponds to the sum of HI plus the rest here. Okay. Okay, so now density evolution is initialized with a Dirac that's centered at zero field with no knowledge about the spin. And we know how to prove that it converges to some fixed point x infinity when you start from here. Okay? So x infinity is always a fixed point when you start from no knowledge about the field. And if you converge to the fixed point delta, Dirac delta at infinite field, then these spins polarize and you can decode. Okay? So the formal definition of the BP threshold is the highest epsilon for which this fixed point here is the Dirac mass at infinity, so that you can decode. And beyond that, you cannot decode with certainty your bits. Okay. Now, this algorithmic phase transition is best viewed on a curve that I call the belief propagation exit curve. Okay, I don't explain the terminology here, but basically, what is this curve? So you consider this BP marginal, and you look at the entropy. So this BP marginal is fully described by this log likelihood that has some density that you find according to density evolution, and you look at the entropy of this object. Basically, it's the average entropy of this BP marginal. So the Shannon entropy of this marginal still averaged over y, and this is this h here. And you differentiate with respect to the channel noise, but you take a partial derivative, not the derivative with respect to the internal dependence here. So that's called the BP G-exit curve. Okay? This BP G-exit curve is exactly equal to the thing that was involved. Well, we'll see later on. It's exactly equal to this partial derivative of the replica symmetric functional effect. So that's a nice object to describe the algorithmic threshold. Below the BP threshold, this curve vanishes, so it vanishes identically, and above the BP threshold, typically it jumps and it doesn't vanish. Okay, now I need to describe this static phase transition, the thermodynamic phase transition. So this description is based on this replica symmetric prediction of statistical physics. So this replica symmetric method allows to compute this functional here. And this functional is written exactly, can be written in terms of these convolution operations that act on densities. So, so the circle convolution is usual convolution. The boxed convolution corresponds to some product of hyperbolic tangent functions and things like that. So you don't have to fully understand this formula, but basically this replica symmetric functional is a sum of three entropy terms. One entropy term is exactly the entropy term that was also involved in the belief propagation G-exit curve, and the other two entropy terms do not depend explicitly on the channel, they just depend on this density x. Okay. Now, when you want to compute this soup, you look at the stationarity condition of the density evolution of this functional, and you get exactly this density evolution equation in the form of a fixed point equation. This was the equation that tracks the BP algorithm, just in the form of a fixed point equation. Okay, so this equation here, if you view it in an iterative way, so it's exactly density evolution, you can also think of it as, well, because this corresponds to maximizing this functional or minimizing minus the functional, you can view this equation as basically gradient descent along this potential. This potential is minus the replica symmetric function. Okay, and when you run density evolution, if your noise is above the BP threshold, you cannot decode because you will get stuck in a local minimum here. Below the BP threshold, you can decode because you go down here. Okay, so now, and the map threshold corresponds to the situation where the minimum jumps discontinuously from here to here. Okay, so it's exactly the situation where epsilon is such that this family of curves here varies such that when epsilon equals epsilon map, this curve touches exactly the horizontal axis and the two minima are equal. So the prediction of statistical physics is that this epsilon map is exactly the epsilon where this curve touches the horizontal axis. Well, it's a prediction, so for the moment I just make a definition. I call epsilon potential this epsilon where the gap here goes to 0. So the highest epsilon such that the gap between the true minima and the local minima minimum goes to 0. Okay, and of course we will prove in the process that really epsilon map equals epsilon potential. Okay, just as I had a BP exit curve, we have a map exit curve, and this map exit curve is just defined like that. You take this conditional entropy averaged over the LDPC ensemble that I'm after, and I differentiate with respect to epsilon. I take the asymptotic limit. Okay, I need a lim sup if I don't know yet that the limit exists. In fact, these limits can be proven to exist at the end. Okay. And when epsilon is less than epsilon map, this curve is 0 because the entropy is simply 0. And when epsilon is greater than epsilon map, the entropy is non-zero. But as I said before, the first derivative jumps, so this curve jumps. And then it's monotone increasing as you increase the noise. Okay. So I come back to this theorem. Now I have introduced a few tools to start proving this theorem. So the theorem that we prove goes as follows. First, we prove somehow that epsilon map, the map threshold, the optimal information theoretic threshold, is equal to the potential threshold that's calculated from this potential function. And once we have proved one, then there is a very easy argument to deduce this equality now. Okay? And as I said before, for many years we have known that the second thing here, we have known that we have an inequality in this direction. Okay, that's the Guerra type interpolation bounds. And this Guerra type interpolation bounds also implies that for the first point you had the inequality in this direction, so an upper bound on epsilon map. Okay, so we have known these two bounds for many years. Okay. So now I'll prove the converse bound for that, and then we can go there. So let me very quickly show why 1 implies 2. Okay? And so I start again with my integration argument just like before. So take the map exit curve. So that's the derivative of the conditional entropy. And now so before I showed how to integrate it from 0 to epsilon. But this does not work when you have a first order phase transition. You cannot go past epsilon map, or even you cannot go past epsilon BP. So now, in any case, since the entropy is 0 below epsilon map, that's not the interesting regime really. So I look only above epsilon map. So let me integrate from epsilon map to epsilon, since that's a total derivative. Well, you find this the function in the derivative minus the function at epsilon map. But at epsilon map, since the entropy just below epsilon map is 0, and since I know it's continuous, this you have to prove independently, then it's 0 at epsilon map. So you just find this. Okay. Now let me take the belief propagation exit curve. This belief propagation exit curve, as I said before, is defined simply as this partial derivative of the entropy of the BP of the entropy of the BP marginal. Okay. Now, if you look at the replica symmetric entropy, if you you cannot remember the formula, but the formula contained this quantity plus two other terms that do not depend explicitly on the channel noise. So the partial derivative will not carry on the other terms. Okay, so you can put here the replica symmetric entropy. And now the point is that you can, since once you put the replica symmetric entropy, since you compute it as at the belief propagation fixed point, and this belief propagation fixed point is also a stationary point of the entropy, you can replace the partial derivative by a total derivative, because the total derivative will act partially on this epsilon, so that's the partial derivative, but it will also act on this x infinity. But how does it act on x infinity? First you differentiate with respect to x infinity, and then you differentiate x infinity with respect to epsilon. But the derivative with respect to x infinity is 0, because x infinity is a stationary point of this functional. So you can do this, and that's where we need technically that the degrees are large, because to play this game you need to control some regularity. How does x infinity depend on epsilon? It should depend somehow regularly on epsilon to be able to differentiate somehow. So that's where we need that the degrees are large. Okay, but once this is done, since this is a total derivative, then it's a good idea to integrate it. And when you integrate it, you find the replica symmetric functional at x infinity minus this replica symmetric functional at the potential threshold. But by definition of the potential threshold, this is 0, because the potential threshold was when this function touches the horizontal axis, where the two minima are equal. And now this is anyway less than the supremum over x of HRS. Okay? Now remember that we had this inequality here that states that the map decoder is better than the belief propagation decoder. That's a completely general inequality. So you take this inequality, you integrate over the interval epsilon map to epsilon and epsilon potential to epsilon on both sides, and you use these inequalities here, and then you get the converse of the interpolation bound. You get exactly the converse of the interpolation bound. So we are happy, because since we have this bound and the converse, which is the interpolation bound, we have the equality. Okay, so I just showed why 1 implies 2. Okay, and now spatial coupling will be used to prove 1. Okay, that's okay. So we just have to prove 1, as I said, and this will be done by spatial coupling. Now, because of the old Guerra type bound, we know that epsilon map is less than epsilon potential. So by spatial coupling, we'll prove that epsilon potential is less than epsilon map. And this inequality is proved for the standard LDPC codes that have nothing to do with spatially coupled codes. Okay, spatial coupling is just a tool that we go around. Okay, so what's the main step of the proof is to construct this ensemble of spatially coupled codes that I vaguely explained before. So we align 2L+1 here ensembles of standard LDPC codes, and we couple the codes in such a way that we create a seed where the bits at the boundary are more or less known. And because they are known, the belief propagation decoder is good at decoding, and there is a decoding wave that propagates through the system. And you can control this process and prove that when the length of the chain goes to infinity first, and then the width of the coupling, so W here is a parameter that measures the width of this coupling. So if you take a position up, this position is coupled up to W position on the left and on the right, say. So when we take the limits in this order, L goes to infinity and W goes to infinity, well, then this belief propagation threshold goes to the potential threshold, okay? So I guess I'm not sure how I'm doing this time, so not very well. Okay, so I'll completely skip this proof. The second element now is to show that for this spatially coupled system, the information theoretic threshold, the map threshold, does not change. Okay. So this we do by a variant of the interpolation method. So we interpolate somehow, I'll summarize this very quickly. We interpolate between this coupled system and a completely disconnected system that's here on one side. And on the other side, we interpolate with another system where the coupling window is as big as 2L plus 1 here. So that's a completely connected system that's equivalent to basically L disconnected systems. And we do this again by some kind of variant of the interpolation methods that you have to hook up. And so we prove that this conditional entropy for the coupled system is equal to the original conditional entropy. So then, of course, the map threshold of the coupled system is equal to the map threshold of the original system. Okay, and so I'll skip the proof ideas of this. Okay. So, and now we put everything together. So that's where things hopefully happen and become clear. So we prove by spatial coupling that the BP threshold of the spatially coupled system is equal to the potential threshold. Now, because this is an algorithmic threshold, it's less than the map threshold of the coupled system. By one variant of interpolation, this map threshold of the coupled system is equal to the map threshold of the original system, which by this old Guerra type bound is less than the potential threshold. Okay? So basically, all these thresholds are equal, and in particular, the map threshold and the potential threshold are equal. Okay? And this ends the proof of this theorem. So since my time is up, I'll conclude here. Now, these ideas can be applied, as I said, to potentially many other inference problems, other graphical models. And we already have some applications to the problems that Florent showed this morning, but we also have some applications to proving lower bounds, better lower bounds for the K-SAT problem. That for k equals 3, these are successful lower bounds that are better than the currently known lower bounds. Okay, thank you.
For k, it's a lower bound on the satisfiability threshold?
Yes. So for k equals 3, we can prove the satisfiability threshold is bigger than 3.67. The previous lower bound in the literature is 3.52.
All right, so maybe we can thank Nicolas again.